Pendulums not stop when they reach equilibrium. The reason is we said the force is 0 at equilibrium. If there's no force, there's nothing to stop it. So there's no net force at equilibrium to stop it. No net force at equilibrium to stop it. I'll actually put it so you can see. No net force at equilibrium to stop it. Okay, so it keeps going. So use your lab to explain whether or not pendulum is affected by gravity. That's what lab B is going to tell us. We're going to finish up lab B next. So is the pendulum affected by gravity? Yes, it is. It causes it to swing. Okay, so what is the equation for the period of a pendulum? So this one I'm just going to give to you. So the equation is period equals 2 pi times the square root of L over G. So capital T is period, which is the time to go once. L is length of the pendulum. And G is gravity. Okay? So what's the length of a pendulum that has a period of 0.5 seconds? So what's the length of a pendulum that has a period of 0.5 seconds? So period, the time it takes is 0.5. G is going to be 9.8. 2 pi is just a constant, so there's nothing to write down for that. And L, the length, is what we're solving for. So 0.5 equals 2 pi times the square root of L over 9.8. All right, so let's talk about how to solve this sucker. So the way to solve it is to get the 2 pi to the other side first. Or if you're solving for period, you would just multiply all the numbers out. But since we're solving for length, we're going to get the 2 pi to the other side first. So we're going to divide by parentheses 2 pi. The reason for the parentheses is otherwise your calculator is going to divide by 2 and multiply by pi, which you don't want. So we're going to take 0.5 divided by parentheses 2 times pi. And that gives me 0.0795774,715. I'll just round it to 0.07 or 0.080. So 0.080 equals square root of L over 9.8. Now, I need to get L by itself, but that square root's in the way. So I'm going to square everything to get rid of that square root. So I'm going to square the 0.08. That gives me 0.0063. And when I square a square root, I get just the things that are underneath it, which is L over 9.8. And now it's an easy algebra expression. You just multiply both sides by 9.8. And you get the length to be 0.062 meters. That'd be 6.2 centimeters. Okay, pretty straightforward. Last, Use a pendulum to describe, in general, simple harmonic motion. So we said simple harmonic motion is any kind of motion that is repeatable over and over again. And a pendulum is an example of this. So what we're going to use is we're going to use the pendulum to give us a general example. So how would we describe a pendulum? So first of all, a pendulum is periodic. So simple harmonic motion is periodic, which means it takes the same time over and over again. So it's periodic motion, takes the same time over and over and over again every time you do it. It's repeatable motion, so you can do it over and over again. And there's a reason why it keeps moving. It has a restoring force. And it has a restoring force to bring it back to equilibrium. So, would a spring be an example of this? Well, a spring is periodic. If you bounce a spring, it'll bounce up and down over and over and over again in the same amount of time, so it is periodic. It is repeatable. The spring makes the same motion over and over and over and over again. And there is a restoring force. There's a force in the spring to bring it back to equilibrium. If you stretch a spring out, it's going to move on its own. That's a restoring force. Well, what about the moon? Is the moon going around the Earth's simple harmonic motion? Well, it's periodic. It takes the same amount of time. It takes about 28¼ days to go around the Earth. So it's periodic. It's repeatable. The moon does it over and over and over and over and over and over and over again. But there's not a force to bring the moon back to equilibrium. Because if I ask you, where is equilibrium for the moon, you can't name it. Right? Where is the natural spot where there's no force? Where is the natural spot where there's no force? I don't know where it is. So because you don't know where it is, it can't be an equilibrium position. Put it in verses. Because you don't know where it is, there can't be an equilibrium position. So there is not a restoring force to bring it back to equilibrium, which means the moon is not simple harmonic motion. It's periodic, it's repeatable, it does not have a restoring force to get back to equilibrium. So that's what simple harmonic motion